For decades, industrial production relied on a simple concept. You start with a solid block of material, and you cut away the waste until you have the part you need. This is known as subtractive manufacturing. Because a machine has to physically reach the material you want to remove, engineers are forced to design every object around the physical path of a cutting tool. If you want to carve a curving, hollow tunnel deep inside a solid object, you quickly run into a geometry problem. A drill bit only moves in straight lines. It cannot bend around corners to hollow out the inside. To get around this limitation, manufacturers take complex designs and break them down into dozens of simpler, easier-to-machine parts. Once those individual pieces are cut, they are welded or bolted together. But every weld adds weight. Every joint introduces a weak point that can fail under stress. And assembling dozens of parts requires massive amounts of time and labor. Traditional machining strictly penalizes complex designs. The more intricate the part, the more it costs to produce, and the worse it performs. To bypass this, engineering required an entirely different approach to building mass. Instead of starting with a block of metal and cutting inward, additive manufacturing, or 3D printing, starts with a total void. Without a cutting tool to accommodate, the toolpath constraint disappears. A digital 3D model is sliced horizontally into thousands of microscopic two-dimensional cross-sections. By reducing a volume into flat 2D shapes, the physical printer never navigates complex internal geometry. It simply draws on a flat plane. Tracing an intricate, maze-like web takes the exact same mechanical effort as tracing a simple circle. Because the machine only cares about placing material on a flat layer, the physical cost of manufacturing geometric complexity drops to absolute zero. While the software slicing concept is identical across the board, the actual physical methods used to build these layers fall into three primary industrial categories. The first method is material extrusion, taking heated plastics or metallic pastes and steadily pushing them through a robotic nozzle to draw each layer. The second method uses light. By shining highly calibrated lasers or UV projectors into a pool of liquid photopolymer resin, manufacturers can selectively cure and harden specific shapes out of the liquid. The third method is powder bed fusion. Here, a laser traces shapes into a bed of microscopic metallic dust, melting the particles together into a solid structure before a fresh layer of dust is swept over the top. Whether the material is extruded, cured, or fused, the result is the same. Accumulating material layer by layer allows engineers to bypass all the physical limitations of traditional fabrication. We can see how this solves the welded assembly problem in the aerospace industry, where extreme heat, massive scale, and structural complexity are baseline requirements. Consider the jet engine fuel nozzle. Historically, this component was heavily machined as 20 separate parts that were carefully welded together. Additive manufacturing allowed aerospace engineers to completely redesign this component. They printed the entire 20-part nozzle as a single, seamless object. This bar chart visualizes the resulting performance gains. By eliminating the heavy internal weld joints, the consolidated 3D printed nozzle dropped 25% of its weight and became 5 times more durable. This geometric freedom has given rise to topology optimization. This is a process where artificial intelligence calculates the exact physical load paths an object needs to endure, and then generates an organic, alien-looking design that strips away every ounce of unnecessary material. These ultra-lightweight, computer-generated structures look like bone or tree roots. They can only physically exist in the real world because a 3D printer can build the impossible geometries they require. Beyond aerospace, the removal of fixed molds and expensive tooling makes mass customization a viable standard, which is specifically transforming the healthcare sector. Instead of relying on standard sizing, a medical device manufacturer can use a patient's CT scan to model and print a custom titanium implant that perfectly matches their unique biological geometry. Traditional mass production requires identical parts to be cost-effective. A 3D printer, however, can produce 100 uniquely shaped dental aligners in a single batch without needing a single tool change. In heavy industry, processes like directed energy deposition take this a step further. Instead of completely replacing worn-out machinery, engineers can print fresh metal directly onto the damaged edges of massive turbine blades. Restoring high-value components prevents them from ending up in landfills. It saves the enormous amount of energy and raw material that would have been required to forge a brand new replacement. By shifting the core principle of manufacturing from subtracting material to adding it, we have replaced rigid physical constraints with a process that is geometrically limitless, patient-specific, and resource-efficient.